think we're all set. Is the VTR on? Okay. I'm sure most of you at one time or another have had the occasion to use a compass. Perhaps, what's the problem? Okay. I'll have to hurry, Al. I've only got 8 minutes yet. I'm sure most all of you, at least at one time or another in your past, have had the occasion to use a compass. It's, of course, made from just a little magnet, and the north end always points toward the North Pole, and you can use it to determine, for example, your way out of the woods or your way on a hike and that sort of thing. Well, perhaps many of you haven't ever thought about whether or not the Earth's field extends far out into space. For example, here we are up in Skylab, some 270 miles above the surface of the Earth, and indeed the Earth's magnetic field does extend out this far, and in fact a good deal further. Well, we can demonstrate that as well, and perhaps you would enjoy seeing such a demonstration. Here's a group of little magnets that I have. These are about 2 inches long and about 2/10 of an inch in diameter. And when we put these just floating out in midair, like I'm doing here, you can see that they take on a very definite orientation. For example, there is one. I've released it right out in the center now, and you can see it is settling down to a specific orientation. That's the direction in which the Earth's magnetic field is running here, right along parallel to this little bar magnet. And we can, of course, use this to determine the direction of the Earth's field right up here at the location Skylab is at. Now, as we travel around the Earth, if we could watch this for a longer period, we would see this little magnet make several rotations as we circle the Earth, because the direction of the Earth's magnetic field is changing. Now, here's another thing that we can do. You see, we must not get too close to it with another magnet, because when we do, the two of them interact, and they very much perturb and influence the other one. Now, let me just make a couple other little demonstrations here for you. First of all, we found, you see, that one magnet aligns very nicely with the Earth's field. And if you watch very carefully, you can see this dipole oscillate back and forth. And I'm removing all the other magnets so that they do not influence it. Now, perhaps you'd find interesting in one of your science classes to try to compute the period of that little compass. Or another way to do it, you can measure the period from this oscillation and compute the strength of the Earth's magnetic field right up here at the Skylab orbit. To do it, you'll need to know a little bit about this magnet, but you can estimate that approximately from the fact that it's a 2-inch long, 2/10 diameter soft iron magnet, and make a calculation to determine what the period of that oscillation should be. Now, here's another little question that might be appropriate for some of the younger members of our audience. Suppose I take 2 of these magnets and I put them together like this. Now, if I put these out here and let them float, you see they have almost no tendency at all to line up with the Earth's field. There's just a little bit remaining, but almost no tendency at all. And so perhaps you can explain that, or if you can't, you can ask your science teacher, and he or she can tell you why it is with 2 magnets like this, we seem to lose that tendency to line up with the Earth's field. Well, we saw the period of one oscillation a minute ago. Let me try it with 2 magnets, end to end like this. Now, you see, they'll also oscillate. It's not like the 2 side by side. 2 end to end will still oscillate. And maybe you can see that. And you can measure this period. And from that period, you could again calculate the Earth's field, or you can determine something about the inertias of these combination of 2 magnets. And I'll leave that for another calculation for your science class. And there is a good view of the oscillation, and in a few minutes we'll zoom in where you can get a little closer look at just what these oscillations look like. Okay? If we could zoom in a little closer now. Okay, now we'll give you a close-up look at the oscillation of one magnet. Put it back in the center. And now we'll use 2 to oscillate. And you see the period of this oscillation is a good deal more slow when we have two of them together. Now, if I put three side by side, we again see they'll have a different period. Now, they move a little too fast there. There we go. And from the observed period that you can see here, you can determine something about the inertias of the little steel rods that we're using. And there's one other sort of interesting thing that's even more complicated. At least I don't have much more than a clue as to why it happens this way, and perhaps you can help explain it. If I put out two of these as closely as I can together, and then perturb it with a third magnet, you'll see that they begin to spin principally about the long axis. There I can make it spin about an axis perpendicular to the rods, but for the most part, they end up spinning about the minimum inertia axis, like that. You'll see it spins about the long axis. Now, alternatively, when I put three out here and align it with the field and then perturb it, I have to bring them back in where we can view it more carefully.
I've used them through Skylab for 4.5 minutes, and we hear you recording or something there, Owen.
I think, Hank, we have channels A and B tied together already, and so I'm just completing the voice part of the VTR tape right now, so you'll probably continue to hear me, but it'll be on the VTR.
Okay.
Three magnets. We see that the principal oscillation turns out to be in a plane perpendicular to the plane of those three magnets. Okay, we'll look one more time at the period of oscillation here for a single magnet. And then when we connect two magnets together, endwise, the period is much longer. And we can extend that even to three rods if we like. And there the period is very clear and can be measured rather accurately. And it's worth a calculation to find out whether or not you can compute how strong the Earth's field is up here at the altitude of Skylab, or you can, if you already know that, you can get the inertia of these rods that we're using as our little compass. Now I'll try this perturbation of magnets that we were looking at a moment ago. And when we put out two of the rods, we know that they aren't going to align with the Earth's field very strongly, but we can perturb them with a third magnet. And when we do, they tend to oscillate about the long, or tend to rotate about the long axis of this pair of magnets. However, when we couple them with a third magnet, so we put the three out here together in sort of a flat configuration, they of course line up with the Earth's field right off. And we try to perturb them with a third magnet, or with a fourth magnet, which we can do. They end up producing a flat spin. And the explanation for that is something that I'm not aware of. And it was a puzzle to me when I first saw it here the other day. And perhaps you can talk that over in your science classes and figure out a good explanation.